When milliseconds make the difference between success and failure, your operating system can't afford to hesitate. That's where real-time operating systems, RTOS, come in. Unlike general-purpose operating systems, GPOS, which aim to optimize overall performance and user experience, RTOS are designed with a single mission: guarantee precise, predictable timing. From controlling airbags in cars to managing avionics in aircraft, real-time systems power critical operations where even the slightest delay can have serious consequences. In this lesson, we'll unpack what truly separates RTOS from GPOS, exploring their goals, behavior, and how they respond under pressure. You'll learn what makes real-time systems unique, why determinism matters, and how these concepts apply in real-world scenarios. Real-time systems go beyond just logical correctness. They must also be timing correct. That means an operation is only considered successful if it happens not just correctly, but also at the right time. A calculation done perfectly, but delivered a few milliseconds late in a hard real-time system could be as bad as no calculation at all. Three foundational traits define real-time systems: predictability, timeliness, and reliability. Predictability means the system's behavior must remain deterministic, even under maximum load. Every task's outcome and timing must be consistent, allowing developers to predict how the system behaves in any condition. Timeliness ensures that each task meets its deadline, strict or flexible, without fail. Missing a deadline, especially in hard real-time environments, could result in system instability or failure. Reliability, the third pillar, ensures that the system maintains integrity across extreme environments and stress scenarios. No silent crashes or memory leaks. These traits make RTOS essential for safety-critical domains like medical devices, automotive control systems, and industrial automation, where timing isn't just performance, it's protection. Real-time systems are not one-size-fits-all. They're categorized based on how strictly they enforce deadlines. The three main types, soft, firm, and hard real-time systems, vary in flexibility, risk tolerance, and consequence of timing failures. Soft real-time systems like video streaming or voice calls aim to meet timing requirements but can tolerate occasional misses. If a frame drops or audio jitters, the system continues operating with reduced quality. Not ideal, but not disastrous. Firm real-time systems raise the stakes. Here, missing a deadline means the output loses value entirely, but the system doesn't collapse. Take high-frequency trading. If a market signal is processed too late, the opportunity is lost, yet the platform keeps running. Hard real-time systems offer zero flexibility. Tasks must complete within their deadlines every single time. Failure is unacceptable and often dangerous. Think of airbag deployment systems, pacemakers, or industrial robot arms. In these systems, a missed deadline can cause physical harm or critical system failure. Understanding this classification helps engineers select the right tools and design principles for their use case, balancing performance with risk and reliability. The core distinction between real-time operating systems, RTOS, and general-purpose operating systems, GPOS, lies in their goals and behavior under load. RTOS prioritize deterministic scheduling and low-latency responses, which means they're designed to guarantee timing precision and predictability at all times. RTOS use priority-based scheduling, where higher priority tasks can preempt lower ones immediately. Interrupt latency is kept to a minimum and is tightly bounded. Context switching is fast, consistent, and often designed to run in O1 time. Memory management is typically static, avoiding the unpredictability of dynamic memory allocation and garbage collection. In contrast, GPOS, like Windows, Linux, or macOS, focus on maximizing average performance and resource utilization. They employ fair or round-robin scheduling, which is great for desktop multitasking, but introduces variable delays. Interrupts may be queued, and memory is allocated dynamically, making context switch times unpredictable. In essence, GPOS are built for flexibility and user experience. RTOS are built for precision and control. If your application needs guaranteed response times, whether it's controlling a robotic arm or managing a medical infusion pump, RTOS is the clear choice. One of the most critical features of an RTOS is deterministic scheduling, the ability to predict exactly when and how tasks will execute. This isn't just about being fast, it's about being consistently fast, no matter what else is happening in the system. Preempt lower priority ones. Unlike GPOS, which may use complex and variable length scheduling logic, many RTOS rely on simple and efficient algorithms like fixed priority preemptive scheduling or rate monotonic scheduling with O1 time complexity. Another key concept is jitter, the variance in task execution timing. In real-time applications, even tiny fluctuations can cause issues. For example, if a signal must be sampled every 100 microseconds, a jitter of even a few microseconds could result in faulty data interpretation. RTOS minimize jitter by ensuring tight control over task timing, allowing developers to meet microsecond level precision. Together, deterministic scheduling and low jitter make RTOS the foundation for time-sensitive systems, where every microsecond counts and reliability cannot be compromised. The RTOS kernel is designed with minimalism and precision in mind, focusing on reducing overhead and maintaining consistent timing behavior. This starts with a lean codebase stripped of unnecessary services or user-facing features that typically bloat general-purpose OS kernels. The kernel supports predictable, low-latency interrupt handling, enabling the system to respond to external signals within microseconds. This is essential in applications like motor control or sensor-driven automation, where delayed responses could lead to instability or damage. A key architectural feature is the avoidance of blocking system calls and non-deterministic memory management. Most RTOS use static memory allocation, eliminating delays caused by heap fragmentation or dynamic resizing. Additionally, many RTOS implement priority inheritance protocols to prevent priority inversion, a situation where a high priority task is blocked by a lower priority one due to resource locking. This ensures that all tasks can access shared resources without compromising the overall timing guarantees. Together, these architectural elements make RTOS highly reliable and predictable, forming the core platform for mission-critical systems that demand both speed and stability.